All right, guys, welcome to another CSR workshop. As you know, my name is Ketki. We'll be conducting the Machine Learning Basics 1 workshop today. Let me know if you guys can hear me on Zoom. Just give a thumbs up or maybe put a yes in the chat. All right, perfect. This is our agenda for today. We'll take a quick look at what machine learning really is beneath all the makeup and the surface. We'll go into regression, which is a classic supervised learning method. We'll take a look at the bias variance trade-off. Then Kashish, my partner for today, will go into the classification algorithms. She'll have a demo on logistic regression. We'll discuss decision trees, and then we'll open up the floor for Q&A. All right, so what is ML? In 1959, Arthur Samuel defined ML as a field of study that gives computers the ability to learn without being explicitly programmed. So, this definition is quite vague. It doesn't really explain what learning means. And as we go forward, you'll understand that learning is just a fancy term for uncovering hidden patterns in the data, trying to understand what the data is telling you, visualizing those patterns, and then using those patterns to predict the future. So an example of this would be, if you had a credit card holder data, for example, if I have a credit card and I have some transactions in my account, and I'm trying to learn whether a transaction I make is fraudulent or not, then we could use that data to figure out, whether this person is really the person that is making that transaction. So if you're using your credit card supposed to make transactions at Ralph's and Trader Joe's all the time, and then in Los Angeles, and then someday your bank finds out that there's a transaction that occurred in, say, the UK, which was like a really large amount, and like it was not the same way that your transactions really are. Like the amount is different, the location is different. Then they can tag that as a fraudulent transaction, and then they can contact you. All right. So learning is conventionally distributed in this 3 different types based on your data. So if your data is labeled, so what does label really mean? For example, if you are trying to figure out if there's a common case where it's like you're trying to figure out if a person who's coming to a restaurant will wait for you to give them a table. Like if the restaurant is typically busy, will they really wait until a table becomes empty, or will they go? So whether the table becomes empty, whether they will wait or not is the label. And what it is dependent on is whether it's a Friday. So if it's a Friday, people are more likely to stay longer, to spend more waiting time, as opposed to if it's, say, like a Monday or a Tuesday. So that's the label. Another type is unsupervised learning, where those labels are not really provided to you by default. For example, with the credit card holder example, it doesn't really come with a label where it's like, okay, this transaction is a fraudulent one. You have to decide whether it's a fraudulent one or not based on the features. And the features there are the location, the amount, the time, etc. And then the third one is reinforcement learning, where this kind of falls out of the typical style of whether the data is labeled or not, because this reinforcement learning is generally used for training agents to say, how the training agents how to act in like complex environments. Okay. Where the agent is trained using rewards and punishments. So, for example, if you're training an agent to play a game, then it's not really easy to, for the agent to have all the information about the environment by default. If it's a chess playing agent, for example, then you can't really expect the agent to, know which chess rules are going to lead it to win. So you have to kind of give the agent the freedom to explore and exploit its environment. So, for example, if it's a given chessboard, and there's only one move left for the player to win, then you give them that reward to make that move. So when the agent moves into that state, they get a reward. As opposed to when the agent moves into a state which does not lead to a win, then you give it a punishment. So in that way, you're training the agent to explore its environment and also exploit the rewards. Within the supervised learning paradigm, there's also a subtype called semi-supervised learning, where all the data is not labeled. Maybe say 30% or 40% of the data might be labeled. So what do you do with the rest of the data? You use some techniques to fill the rest of the labels yourself. So that comes under semi-supervised learning. All right, so let's treat supervised learning in a more mathematically convoluted way. Let's say that you have some data examples, x1, y1, x2, y2, up to xn, yn, where x1 is your input. So your input will have up to d features, and y is the outcome measurement. And your goal is to learn a predictor that can predict the outcome y for some unseen example using these given examples. So the x's are also known as independent variables because they're not dependent on anything. They're not related to each other or to the outcome variable or the input or the regressor. Now, because y depends on the features, which is the x, it is known as a dependent variable. It is also known as the output or the response. And the predictor that you're learning, which is f, is the machine learning algorithm or model. Now, depending on y, supervised learning can be classified into two further types. If the y is discrete, then you have a classification problem on your hand. So what does discrete mean? It's like if it's binary classification, it's going to be +1, -1. By it, I mean the label. If it's say some other problem, for example, spam mail detection, then the labels are going to be spam or not spam. And if the yi is continuous, which means it's a real number, then the problem is called regression. And an example of this would be stock price prediction, because the price is a continuous number, it's not discrete. Now, within unsupervised learning, we have no labels. So we can't really predict a label per se. What we are more interested in trying to do is trying to group the data based on similarities within the data. And that this is a common problem because it's often hard to find label data. Most of your data, you'll see that it's really unstructured, a lot of missing values. So expecting the data to be labeled is kind of it's kind of difficult. Now, dividing the data based on similarities into subgroups is called clustering. The groups will be called clusters, and your goal right there is trying to have the members of a cluster be as similar to each other as possible, and you want the clusters themselves to be as dissimilar as possible from each other. Another application of unsupervised learning is feature engineering, which we achieve through dimensionality reduction. So you'll come to know that a lot of your features, they're just like redundant. They might be highly correlated to each other, in which case the machine learning model that you're developing, it might be unstable due to that correlation. We'll see an example of that. So what you want to do is kind of reduce these features. You want to eliminate the redundancy, and that you can achieve through dimensionality reduction. All right, so this is kind of a summary of everything that we covered. If you have labeled data, then you can go into supervised learning. And depending on the type of the label that you're trying to predict, if it's a category, then you'll be using classification. If it's a quantity, then you'll go into regression. If you don't have labeled data, then of course it's unsupervised learning. If you're just interested in grouping data into different groups, it will be cluster analysis. And if it's feature engineering that you want to achieve, you'll be using dimensionality reduction. Now let's see reinforcement learning really quickly, because it's not a point of focus for this workshop series, but let's just see what it is. In reinforcement learning, you have an agent. So this agent can be, say, an autonomous vehicle. And you want to teach it to navigate environments without explicitly telling it what to do. So what you'll try to do is, you don't really know so let's say you have a car, and that car needs to drive straight on the road, and it needs to make a a left. You want to tell it the right way to make this turn without, say, hitting someone, hitting the side of the road, hitting other vehicles. You want to have it follow the traffic rules. So if it follows, so if the red lights comes on, and if it stops, then you give it a reward so that it repeats that behavior. So all these rules, like trying to tell it to maybe swerve 5 degrees to the left, is really difficult to program. And if you start writing these rules, then it's going to be really difficult, because it's going to be like 10,000 lines of code, and it's going to be really hard to maintain. And you can't really predict situations. You just have to give the rewards and give the punishments in such a way that the agent is incentivized to maximize its reward. All right, so let's take a look at linear regression. It comes into really simple 3 steps. You get your sample data, you design a model that works for the given sample data, and then you use that model to make predictions on unseen data. Now we'll take a look into the different types of linear regression. You have your input variable, which is X. It's going to have D features or D variables. So for example, X1 can be location, X2 can be amount, X3 can be time. If you only have one feature, then it's going to be simple linear regression. And the equation that we're trying to work with is y equal to beta 0 plus beta 1x plus epsilon. So what are all these terms? Y is our prediction. Beta 0, beta 1 are called regression coefficients. X is the independent variable, and epsilon is the noise. So in this equation, just let me know, like, what all do we have and what are we trying to find? Any guesses? Yeah.
Find out the coefficients that give you the best dependent variable based on the independent variable.
Yeah, exactly. Yeah, exactly. So we have X and Y from a training data. We are trying to find beta 0 and beta 1. And epsilon is noise. It's a term that is unaccounted for. You realize that no matter how perfect you're trying to make your algorithm, it's never going to be perfect. It's always going to be some sort of error that you can't really explain. And that can be encapsulated in the epsilon term. All right, so this is a representation of how the linear regression algorithm really works. You can initialize beta 0 to beta and beta 1 to any values. Of course, there are some methods that will help you, get your optimal model faster than other initializations. But mostly what it's trying to do is it's trying to fit this line to your data so that your predictions are as accurate as possible. And what do I mean by accuracy? We're just trying to minimize some error, which is a performance criterion, you can say. Typically with linear regression, you'll be using mean squared error. So you'll predict some y, and you'll use a y that you already have. You try to compare those two y's, and that is your mean squared error, and you're trying to minimize that. All right, let's look at a demo. Okay. So let me share this with you. You can make a copy of that and work with it. Let me know if you can access it. Can you guys open it? It's okay, cool. So here we just have all our imports. Today we'll be working with stats models, which is a Python package, and we'll be using OLS from it, which is ordinary least squares. These are just like plotting methods. We have some pre-processing and the mean squared error function. All right. So what I've done is I've taken a data set from this URL right here, and I've added that file to my Google Drive, and I am mounting it right here. So now that file is accessible to my Colab. We'll be reading that file. This is just an explanation of what the file is. So we have 4 features, which is a temperature, exhaust vacuum, pressure, and humidity. Yeah, and we're trying to output the electrical energy output of a plant. So the PE is our target, which is our Y, and this is X1, X2, X3, X4. We have like 9, 5, 6, 8 rows and 5 columns. This is just a pair plot I created to visualize that data. So I'm trying to find out if these features have like a strong correlation with the Y. So a good question in machine learning that we should always ask is whether the cause-effect relationship that we're trying to find is really present or not. Like it's easy to say like your height and weight are related to your age in some way, but studies have found that that's not really true. But you know, a machine learning scientist can always find some correlation between them, but that doesn't actually exist. So from here you can see that AT and PE have a really good correlation, although it is negative. That's still fine, but there is a correlation. V and TE have a slightly weaker one, but it's still present. And then AP and RH, they're really scattered all over. So we'll try to investigate whether they are actually good predictors for the output or not. Now here what I'm doing is for each of these 4 predictors, I'm just creating an ordinary least squares model. So ordinary least squares is just like the performance measure that is using is least squares, which is what I said, it's mean squared error. So within this model, when it's trying to fit the line to the data, the performance criterion that it is using to know when to stop is least squares. So within least squares, you need to provide an R style string, which is like, the string is like PE. Just write it. So you need to provide a string like this to tell OLS what to use as the Y and what to use as the X. So that's what I'm creating right here. And I'm providing the data frame as the data. And this is just where I'm instantiating the model, and the dot fit is the method that I'm using to fit the model to the data. We get our results, and I'm printing a summary of that right here. And then now I'm just storing the coefficients for reference later on. And I'm plotting the model right here. All right, so let's take a look at these results. PE is the dependent variable, OLS method is the least squares, number of observations, all this is all right. A really important term here that you want to know is the P. So P value is it's related to hypothesis testing. I want to explain it in short, but not go into too much detail because it's like a lot of math. What we want to do is, so in the hypothesis testing, there's a value called alpha, which is like the type 1 error that you can set to check whether your model performs well or not. So I want to give you an analogy that one of my professors gave me. If you're in a courtroom and you're a judge and you want to maybe prove someone guilty. So you want to set some threshold for which, like, if you have that amount of evidence, if you can say with that level of confidence that the person is guilty, then you can convict them. Otherwise, they're innocent. So the alpha is that level of confidence. It's going to be, generally we set the alpha to 0.005, which is like 0.5% or 0. Yeah, sorry, my bad. It's 5%. It's not 0.5%. So you have to be able to say with at least 75% confidence that your feature is actually related to your output. So this p-value, it needs to be less than 5%. Only then can you say that your feature is actually related to your y. So we can see here that for all of these, for all the four variables, the p-value is, of course, less than 5%. So we can say that these features are statistically significant. We can actually move forward with these features. Like, we can actually try to improve our model using these features as well as their interaction terms, which we'll see later. But if it was greater than 5%, then you can just go on and eliminate that feature completely. You don't need to consider it any further. And these are our betas. So since this is right now, I'm just trying to fit a feature by itself to y. It's just going to be like, this is just going to be beta 1, and this is your beta 0. Excuse me. The next very important statistic that you have here is the R squared, which right here is 89%. So R squared is the amount of variation in your data that can be explained using this variable. So right here we have a temperature. So we can say that temperature is able to explain 89% of the variation that occurs in the electrical output. So that's a very good percentage, right? It is quite high. So that means that it is actually related to your output variable. You can try to take a look at the rest of these. They're really mathematically intensive, trying to understand the F statistic, T statistic, and we can like have an entire workshop on these themselves. I'll try to add some resources later on for you to understand these better and explore them. So here you can see that the regression line is plotted. This is our data again. So here we've clarified that these are actually like statistically significant, but since the R squared value is quite low, right, for pressure as well as for RH, so the model might be underfit, which means that it's not really able to explain why the Y is the way it is based on these features alone. We might have to consider some higher degree features. So now I've gone forward and created a multivariate model where I'm considering all these four, right? There is the R style string. Trying to consider all the four features together and trying to fit them into one model only, and then checking if that model is good. So yeah, see the R squared value about 92.9%. It's pretty good. So now a question that I have for you is, as you can see here, the coefficient that we found for the univariate models, they're different from the coefficient that we found for the multiple regression model. So can you explain why? I'll try to give you a hint. Yeah, this is the equation that we use for the multivariate model. Yeah.
I believe you're only like finding the coefficients between that one like input and that one output.
Yeah.
But with the other ones, you have to take everything at the same time as this one. So you have to
Yeah, perfect answer. All right. So now the next question that we need to ask is, how many features is too many features? And what degree polynomial do we actually need to consider for, my bad, I need to explain this. Sorry, my bad. Yeah, so now what we want to do is see if any higher degree features can explain this model even better. So now what we do is we're trying to take like the squares of these and the cubes of these. We're trying to add them as features and we're fitting a model on that. So as you'll see from these results, it's really not doing that much better than the other models. What another experiment that I did is I consider the interaction terms as well, wherein I consider like these two together. So I multiplied the temperature with the volume, multiplied temperature with the pressure, and I consider these. And this one did do better than the just like the 4 features on their own. So the question that we need to ask is like, when do we stop? When does this stop? Do we stop at volume raised to 4, volume raised to 5? How high should a polynomial go for us to be able to find a good model, and where do we find the stopping point? Which is where this concept called as bias variance trade-off comes in. So let's take a look at these graphs. On the left graph, we have the black truth, which is our actual model, which is of course not apparent to us when we're doing this, because the entire point of this process and this activity is trying to find this black curve, right? We don't actually know what the ground model is, and we're trying to find it. So we start with our basic univariate regression model, which is the orange line. It's just a 1 degree polynomial. And then we try to add quadratic features, and we try to add polynomial features, and that's how we get the blue and the green curves on the left-hand side. And on the right-hand side, what I've done is I've divided my data set into training set and test set. And the red curve is the mean squared error for the test set, and the gray curve right here, it is the curve for the training data mean squared error. So as you can see here, for the orange model, both the training mean squared error and the test error, they're quite high. And as we go on increasing the complexity of the model, which is the degree of the polynomial, the training error will go on decreasing. And truthfully, as you can see here, it's never going to stop decreasing, because training error, like the more complex is the model that you make, it's just going to get even more fitted to the training data. It's just going to learn the training data more and more. It's just going to be like, for this sample, this is the label. So for the next sample that looks exactly like this, that will be the label. So it's becoming less general and more overfit to the training data. Whereas you can see as the flexibility of the model goes on increasing, as the degree of the polynomial goes on increasing, the test error, it's going to achieve some local minima, and then it's just going to shoot up more. So why does this happen? Like I said, it's learning the training data too well. It's like it's not able to generalize well to unseen data. Of course, when you test your model on unseen data, your unseen samples are never going to be exactly the same as your training data. So it's just not going to be able to perform as well, because it has only learned, like it has basically learned rules. Like if x is 1, x1 is 1, x2 is 2, then the label should be 3, which is not what we want to do at all. We want to make the model as general as possible. So how to find this sweet spot right here, the blue dots? How to find what is the right level of flexibility? That is where the bias variance trade-off comes in. So you experiment with your flexibility, and you try to find, like, there's this process that you do where you increase the model's flexibility iteratively. You try to add features slowly and slowly until the training error and the test error, they come to their local minima. So like if the test error is shooting up, you're gonna stop your training right there. That's the highest level of polynomial that you should go. And that is where you should stop your training, which is where you'll find like the best model that you can achieve. So the bias is related to the training error and the variance is related to the test error. If your bias is high, that means that your model is underfit to the training set. I mean, it's not performing really well on the training set itself. So how can you expect it to perform well on the test set? But if you don't want to go too deep into the overfitting, and you eventually get, a very low bias where your model is performing really well on the training set. It's like 99% accuracy, but it's not going to be able to do well on the test sets. Yeah, that's all I had. Yeah, this is where I demonstrate the training and testlit. So I'm using this function to split my data into training set and test set. I'm using a 70-30 split. So 70% will be the training set size. Yeah, I'm training a model on that with all the predictors, and then I go on ahead with the polynomial features as well. And there's a small to-do for you here. Yeah, so this is the, at the very end, I have this model that is including the polynomial features with the interaction terms. So interaction terms is just the multiplication of the features. And what you need to do is, like in your spare time, whenever you have time, you can use this model to predict on the test set and find the mean squared error, and then just, like think about why this is performing better or worse than just a simple model. I'm gonna pass on over to Kashish, who will go into classification. Thank you.
Hi everyone. Let me just set things up in a minute. So I think I had a video for you guys just to give you. Oops. It's because of this. It's fine. Yeah. Okay. So I think we had a video by Google, which was like posted 7 years ago. And I just wanted to show you guys to know why this actually came into place, because I think you guys have programming background, but I think it wouldn't be more like, why this started. So you can just say like, maybe you can have a lot of like if else and for loops, and people can actually decide on their own things. So for example, if I want to make a tic-tac-toe, right? So we don't really need an algorithm to say a machine learning algorithm to learn how to play tic-tac-toe, and then you do that. You can have an if else loop, and you can just carry forward and hey, if this place is empty, then you put something here, and it can be like a complex program, but it does not really have to be like a machine learning algorithm altogether. But just to get you started, I think we'll just start off with the video, and we'll just jump right into why do we really need this thing, and why did we really go through, say, linear regression, and why are we really starting out with, say, test data set, other data sets, and why do we really need to think that way, and how it has all transformed into, say, ChatGPT right now, and how that particular thing is working, and where do you want to have your base set up so that you can contribute towards cool machine learning algorithms and build something cool. So I'll just start the video up. Let me just go back. Here you go.
There have been a number of shifts in the way we think about computing over the past few decades.
The terminology artificial intelligence has come in and out of favor in the scientific community. Sometimes it's called machine learning.
We tend to call it machine intelligence these days.
I as well. intelligence. I just call it intelligence. And sometimes it's just the effort to build machines that are better.
So in the early days, everything was built on logic, doing mathematical integration problems, playing chess. We realized that what the real challenges were the things that people can do every day.
The real world is actually very messy. Hard logical rules are not the way to solve really interesting real world problems.
You have to have a system that will learn to get knowledge. You can't just program it all in.
Artificial intelligence is an effort to build machines that can learn from their environment, from mistakes, and from people.
And we're still at the stage where we don't know what is the right path and the right breakthrough.
So, I mean, there's certainly a whole raft of different approaches.
One of the subfields we call pattern recognition.
Artificial neural network,
Reinforcement learning, for example.
statistical inference, and probabilistic machine learning.
Supervised learning, unsupervised learning, and we're not quite sure what technique is going to lead to better systems. And in fact, it's probably not one technique for everything. It's probably a bunch of different techniques and combinations of those techniques.
Any progress we make in building truly intelligent systems is going to depend on progress in technology generally. But until recently, we didn't have computers that were fast enough or data sets that were big enough to do that.
And so being able to take a particular problem, spread it out over lots and lots of machines is a very important approach with the mix of research as
So there's applications of artificial intelligence around us all the time.
When it begins to work, or it does work, it's all of a sudden given another name.
We're all already using it and very comfortable with it.
Things that now we regard as routine, 30 years ago would have been regarded as amazing examples of artificial intelligence.
Anti-lock braking,
Autopilot systems for planes,
Search.
recommendations.
maps.
To decide whether or not this particular email is spam or not spam.
the ability to translate one language to another with your phone. 10 years ago, if you tried to talk to your computer or to your phone, that would just be hopeless.
We are seeing a steady torrent of these tricks one after the other getting figured out right now. And I think a lot of people that are close to the field have this, do have that kind of breathless sense that things are moving quickly.
It's a progressive thing. It's about building things that are slightly better, slightly better, slightly better.
Intelligence is really not going to be something that we ever succeed in defining in a succinct and singular way. It's really this whole constellation of different capabilities that all kind of are beautifully orchestrated and working together.
Predicting the long-term future is very difficult. Nobody can really do it. And I think to do is take whatever's working best now and assume the future is going to be like that forever.
I think that pretty much summed up, like this was like 7 years ago. So just imagine like how Google was thinking, like, how artificial intelligence and machine learning would actually change things. And 6 years or 7 years later, I think now we have Bard and ChatGPT fighting each other, and we're like way too ahead from what actually was predicted here. So just to come back to the slides that we had, and before I get started with, say, classification algorithms, I'll just let you know how the machines really think and how you are making them learn through different techniques. So say, for example, if I say that, somebody who writes a letter A would be different than maybe how you write a letter A, right? And maybe that person writes a letter A in, like, say, all caps or in all, say, bold letters or something of the other sort. So how would, like, say, when Apple was creating the, have you seen in your gallery kind of thing, if you open up an image and you long tap it, you're able to copy the text that you've handwritten. So how do you think that algorithm was able to know that you wrote an A and maybe she also wrote an A and maybe he also wrote an A? So what happens actually is that, you provide some input and the machine actually notices, okay, so this letter which she wrote is actually an A. So she told the machine that, okay, this letter means A, learn that this means A. And you told your machine that, okay, this letter means A too. So so basically, like, the machine is like mapping every letter, which is like going towards the same value. Just like I think she told in linear regression, you have that value Y and you're mapping everything towards it. So at the end of the day, I think it will be like, say, 50, 60 kind of A's that people can create, and machine has already learned and seen that this is how this A is mapped. And for all the alphabets, this has been done. So now what happens is that maybe this guy right here, this person's handwriting is not known to machine at all. So this person is not in the training set. So what we try to do is that this person will actually be in the testing set, and he'll be writing like A, B, C, D, or maybe his own name, and the machine will actually be able to recognize what he has written. So how will that machine perform is depending on how the model was fitting. So what this model means is just mathematics. So if you have a curve, right, like I think this graph was right here, this graph. So all these data points, right, say for example, all these data points are like mapping onto something. So this graph is something which a model is fitting into. So maybe like letter A, like say for example, this thing means that this is a letter A. This means that this is a letter A. So all these data points, right, it's fitting well in this curve as compared to this curve, right? So maybe this model is doing better as compared to that one. So I think that is how we are basically judging what model to fit in. And in this, basically like the intro workshop, we'll be going through like some different kind of models, and then later on we'll be learning more difficult models, how to implement them, how to create them, and how to build your own machine learning systems. So I think that pretty much gives you an idea of what training data set looks like, what testing data set looks like, and how machines are actually thinking. So I'll get on to the portion where I have to talk about the classification algorithms. So in this slide, right, if you just see email as spam or not spam, transaction as fraudulent or non-fraudulent. So what does this basically mean is it's like a yes or a no, 0 or a 1. So you're just classifying things into two certain boxes. So if I say there's a box of say red and blue balls, and there are two boxes there, one is like a labeled red, one is labeled blue, and you have to put these balls into these different boxes. You have to label the data set into different items. So this is what you're making the machine learn. So this thing is called a classification algorithm. And since this covers under supervised learning, what does it mean that you're supervising it? So you're telling the machine that, hey, this color is blue, put this into blue. This color is red, put this into red. And now the machine will learn that, okay, let's pick a ball and then judge what, if this is a blue, we'll put it into blue, because this is what we were told, right? That this is blue and you have to put it inside the blue thing. So this classification algorithm comes under supervised learning, and we'll be learning how classification works in real life scenarios. So here in the first case of example, we have like email as a spam or not spam. I think we'll be going through this example as well in Python Colab notebook. And the next thing being say transaction is fraudulent or non-fraudulent. And then you can actually go further into say between two items, you can have like multiple items and then you classify into different things. So you can have like an image of say a cat, and the model has to recognize whether it's a cat or a dog or a giraffe or maybe a tiger. So you give like 4 classification and it has to choose which image it belongs to. So I think that's a broad idea of what classification means here. And then let's say, yeah, looks good. So how to solve classification problems? So you saw the linear regression model, right? So why don't we just use linear regression and solve the classification problem and not just like introduce something else? So I tell you why. So in classification algorithms, I told you it's either a yes or a no, either a 0 or a 1, right? So in this graph, if you see, the red points are 0 and the blue points are 1. So if I have like something on the x-axis and then, you're predicting something on y-axis, I've not mentioned it here because it's not really relevant for you to notice how the classification is working. But if you just see on a broad scale, you just have 2 values, right? You won't have that entire graph thing that we had in linear regression sort of thing. You won't have a long curve or a sigmoid function or something of that sort. It's just like 2 different values here. So if I try to use linear regression and I pass this data, 0s and 1s into a model, so maybe it will create this line sort of a thing with us, and this would be the slope of the entire model, and we can just predict through it. So if I need to say that maybe at this point of time here, I need to predict what would be the value at this 0.5. So it's saying that it's here. So this median would mean that this is a yes and this is a no. So here in this classification, you're able to say that, okay, if the value is below 0.5, everything would be a 0. And if it's above 0.5, everything would be a 1. So here linear regression is fitting. But the problem comes when you actually have to say, you have another data set coming in. So you can't justify what kind of a training data set you have. It could be clean, it could be as messy as this one. So when that last data comes in, that's also equal to 1, but it's like way too high on the X value. So now what will happen is, when you try to train on this kind of a data, the slope will change. Now, as soon as the slope changes, you'll see that this point where you had, say, 0.5 portion coming in, it will actually be this newer slope which is coming here. Now, as per this slope, the division would be this straight line. So this straight line, if I just draw it in this way, then that means these 3-4 data sets as well, which were actually true, like it was actually 1 here. Now they are being segregated into 0. Like here, if I have a slope of this is greater than 0.5, then y equals to 1 as y equals to 0, right? So basically what it's trying to do is above this line, like after this line, it's saying that all this is 1, but before this, right, all these red dots as well as these 3-4 blue dots, right, they're all being classified under 1, which is incorrect. So linear regression is kind of like failing here, and we're not able to classify different things when we have a huge data set. So that's why I think we're not really, so in industry, we don't really use linear regression to solve classification problems. So how do we actually solve logistic regression models? So there's this function called sigmoid function, which is like purely mathematics. If you've done maths, I think you know how this slope looks like. But just to cut it short, it basically has this kind of a slope. And whenever you compute the h value that we were computing here, when you try to compute this here, it fits better as compared to getting all the values in between from here to here. And everything below 0.5 is going towards 0, and after 1 is going towards this. So logistic regression is just another mathematical function which you kind of have to use in order to solve the classification problem. It's not like linear regression. It's just the formula change. So when you had y equals to say mx in like a linear slope that we had in linear regression, here we just have the sigmoid function. So just an example here, what I told you, right? It can be 0 or 1. You can have 3 different categories, say cat, dog, and tiger, and then you can go into more. And then the difference between multinomial and ordinal is that sometimes when you divide categories, they're not in any order. So you can have like say cat, dog, any kind of an animal, and they're all on the same level. Whereas if I say that if the risk of some disease being caught to a person is low, medium, or a high, so they're all in an increasing order or a decreasing order in the range of the classification. So it matters that at that time the order matters. So it's like an ordinal logistic regression. So just the different types of how logistic regressions come out to be. Okay, so this example that I created is just the email spam detection sort of a thing. So it's a very small example and it's pretty basic. So when we just started off, I think if you know Python, I think you'll be able to understand this very clearly. I'll just wait for it to load. Okay. So just don't go over the import statements and all the libraries that we have used in machine learning. We have different libraries, say pandas, numpy, and all these things, just to have these mathematical formulas there. Once you get started with Python and once you start creating your own machine learning algorithm, starting from the basic, you'll be able to understand these better. So here in the first line of this Python code, I'm basically trying to read the CSV file. Now this CSV file kind of like looks like this. So if I have an email text here, say somebody sent an email, and this person said that this is really not a spam email. So you have already given that, was this a spam email or not? So this is a spam, this is not a spam, this is not a spam. And you have like say a 500 or a 400 line Excel sheet with 2 columns. One of them is like defining whether it's a spam or not, and the other with the content of the email. So this is the data set that we have, which we want to train our model on, we want to test it on as well. So what I'm trying to do here is, say, for example, like I told you about the handwriting portion, I divided you people into 2 groups, into testing and then training set. So he was one of the testing people and you all guys were in the training portion. So as I think the common sense goes that you have a larger training set so that the model can learn better, and the testing portion will be slightly smaller so that you just need to test things out whether it's working fine or not. So what we're trying to do here is we'll just divide this into, this is like 100% data set. So we'll divide it into 80 and 20. 20% would be the testing set and 80% would be the training one. So what I'll do is from the first line to the 80th, like say 80% of the lines will be sent to this model, and the model will learn, okay, this content of the email was so and so, and this was a spam and this wasn't a spam. So machine is not doing anything, it's actually learning. So it's just noticing what the words were. So maybe if somebody had like you won a lottery ticket, so this lottery keyword will come twice or thrice in like different spam emails, right? So the machine will notice that this lottery keyword is coming multiple times. So maybe next time when I see an email and it has like a lottery keyword, then this has to be a spam. So that is what we're trying to make the machine learn. So here, this df.head is nothing, it's just displaying the data in front of us. And if I just go a little down here. So we're just trying to drop the columns and just rename the table as label and in text. We're just setting things up. This was actually like unnamed column name and column name. So we just sent a label and a text here. But after that, if I say, so here we created a map sort of a thing. So we are just mapping into zeros and ones. So since the model is like understanding zeros and one, as I told you, the computer is better able to understand instead of like the spam and non-spam text. So what we try to do is whenever it wasn't a spam, we put a 0. And whenever it was a spam, we put a new column as 1. So that is the only mapping that we created here. So right after this, I think we're just trying to count the values of how many spam we had and how many not spam emails did we have. And then finally, we created this sort of thing where we're actually tokenizing things, we're processing the emails. So what happens is the email can have a larger text and some emails can have a smaller text. So what we're trying to do here is like not every word matters in detecting whether it's a spam or not. Like I said, the word lottery might mean a lot more than as compared to the word the, hello, or like hey, or a person. So these words are just there to support like maybe verbs or something else, but some words are actually very important. So we're just trying to extract those features, finding those things. You can just skip these things if you want to. But when you come here, so here is the portion we're actually training the data set. So what we're trying to do is we're trying to use logistic regression. Where's the cursor? Hold on a sec. Let's see. Yeah. So here, if you see, this is the logistic regression that we're trying to use. This is what matters to you because this is what we're learning today. And then we're trying to train the data set and we're trying to calculate what the accuracy is. So what happens is that we're trying to use this test data set of 20%, and the total was like say 10, and then 0.8 was the training data set. And then finally, we were able to train the model. And then at the end of the day, the training accuracy was 98.60%, the validation accuracy was this much. So what does this mean is that when we try to have the first 80, suppose we had 100 lines of 100 emails. So first 80 emails were given to the model learned whether it was fraudulent or not, and it basically learned how to detect spam and all. And then finally, the last 20 lines were provided, and we were checking. Say the model predicted that the last email was a spam, but actually it wasn't a spam because we gave the data at the beginning. We had the Excel there, so it was able to detect that if the accuracy was in the range or not. So we had like a result of say 98 or 96%. It's pretty good in that sense. So logistic regression works for say classification of emails into not spam and spam. But sometimes when you say that, say, how does Gmail actually verify that your email is a promotional email or a social email or something else, like you have different classifications there. So they dive deeper into these kind of models, and instead of like using a general logistic regression, they're using something more complex there. They're using multiple types of parameters instead of like just telling that this was a spam or not. They basically have like multiple columns saying what parameters were in the email that made the email go into this kind of a thing, and from the, like maybe the sender had a different kind of an email address. It wasn't from an edu. So like in our email addresses at USC, everything that comes out of the edu email addresses, they go into spam. So that is how the system is working in the Gmail for our organization. So that's a general sense of how things are working. I hope it's clear, but we'll take questions at the end. So yeah. So I think one more thing that we have, just like similar to how we had the classification thing, we have decision trees. This is also part of the classification thing, and it's pretty simple to how you draw if-else statement and how you put your algorithm into use. So if you remember in like any of the CS classes that you might have taken at the beginning, instead of like beginning to code, you write algorithms and you try to have those flow charts. So if it's like you draw like if I equals to 1 and then yes and a no, and then you map things together. So similarly, we have decision trees. So it's basically to understand how the prediction and classification would look like. So I'll give you an example here. Say, for example, you had some work to do and you have to decide whether you want to stay in or go for movies. So that end portion is like the, say, go to beach, go running, stay in, go to movies and stay in are some of the things that you have on your list, and you can choose what to do because you're free right now. So if you start thinking what to do, is like yes or no, if you want to stay in or if you want to go and do something outside or outdoors. So then if you decide to stay in, then you're just staying in, it ends. That loop has ended, those conditions are done, decision has been made. But what if you decide to go out? Then you choose this outlook sort of thing, and then you decide how the weather is looking, what the day is, how the outside environment is, and you make some decisions on the basis of that. And then maybe you check whether your friends are busy or not. So just like how the decision making thing goes in like your if-else statement, this tree goes in like machine learning algorithms. and you try to decide whether the machine has to dive deeper into things or it has already made a decision. So you go through the parameters yourself, and these are the things that you actually define yourself, and your machine learns through this model itself. So it's like a pretty simple version, but yeah, it goes more complex than this. So some of the weaknesses for decision trees are more like, see, when you have more classes, so here I think we just had like the outlook and then what to do and then fetch busy. So these are the 3-4 outlooks that we had. But sometimes in real world scenarios, they are like more complex. So drawing these huge decision tree diagrams and then coding into a Python script or something of that sort is pretty complex. And then you have to figure out where the things are going and whether it's going in the right direction or not. If you just remember how in CS classes, people tell you not to use if else loop every single where and use switch cases and all these things because the code is very messy and very long. So just how that thing works, I think the decision tree algorithm is not really favorable in that sense because it kind of like makes it a long code. And then it can be computationally expensive to train. This is because everything has to be sorted before. So you have to decide whether this or that, whether this or that. And it's not really possible in real life scenarios to actually diverge different things. It can be that person really wants to do this, but he or she is confused between doing this too. So you have like two things which have equal probability coming in, and you're not able to make a decision on the basis of that. So that, and in those type of scenarios, I think this is pretty expensive to train because you have to make the machine know different kind of data set and choose what to do. Now, in this session, we just covered logistic regression and decision trees in classification because I didn't want you to be, say, burdened with how broad this entire domain is. But in general, we have random forests, support vector machine, k-nearest neighbor, name base, all these algorithms exist. These all are mathematical in nature. They have all these algorithms that have already been defined, and you just have to see like whatever problem that you're trying to solve, is that solvable with this model better or that model better? So what people and like machine learning engineers, they do, they try to fit, like they choose, like say the first 3 models are maybe better for my code. And then they try all these 3 models and they judge what the prediction accuracy is. And whoever, like whichever model has the higher, they choose to implement that particular thing. So suppose like you all are working at maybe Google and you all devise an algorithm to classify your emails into spam or not spam. So maybe she came up with an algorithm which was using k-nearest neighbor. So she tried to use this algorithm, maybe use something else. And then finally, when I was the product manager of the team and I chose that maybe because her algorithm has like more features and I can like scale it better with like millions of users out there, and this can be, you know, feasible for us and has a better prediction accuracy. So we'll just go forward with that. So at the in the video too, right, you saw that no algorithm or model is like perfect in that sense for a particular problem. It just needs to be trained, devised, and written in certain ways so that it fits that particular thing better. So just a heads up here, you can explore these things. We will be having more workshops on machine learning. So I think other people will be able to dive deeper into these better. But then, yeah, this is like a broader area of what classification looks like. This is all supervised learning itself. So we had linear regression and then we had the entire classification portion. So this is like a very basic discussion, but I think we went a little deeper into the session itself. But the first question here is that you have a large inventory of identical items, and you want to predict how many of these items will be sold over the next 3 months. And the second one is you would like a software to examine individual customer accounts, and for each account to decide if it has been hacked or compromised. So would the first problem or second problem be a classification or a regression? So I think I'll just leave it up to you, and if you have any, if anybody wants to volunteer and answer the, like, classify these 2 things into regression or classification problems, I'd be happy to see. Yeah, go ahead.
I guess the first one is if you want to see how many people that would. The second one is probably the classification, which I think is one pack classification.
Which one is it? Yeah. So in the first one, you can say that, you know, when you're predicting how many of these items would be, it's like a linear or say a continuous value. So you can have like say 10, 11, 11.5, 12.5, 13, 14. So it can have a broad range of numbers. There's no upper limit or a lower limit to those values. So that's why linear regression or regression fits the first one better. But in the second one, it's either hacked or not hacked, either compromised or not compromised. So that's why it's more like a classification problem in that sense. So these were some of the resources that I could find, and many people who are getting started with machine learning use. So the first one is the Stanford AnguNG cheat sheet, and that's like the best resource which is out there. It has been there for a very long time, and this is specifically to the supervised learning. So whatever you have learned today, starting from linear regression to logistic and then classification algorithms, which I discussed and did not discuss, you'll find them on these cheat sheets. The second one is again a replica of the same, but it has like a broader classification of what model to choose when. And then here is like a Google's machine learning crash course, which is like again very famous out there because it has like hands-on sessions for you to just practice whatever you're trying to learn. It has like sample data there and you can try and train these things. So this crash course, I think, is not more than 15 hours in total. So I think you'll be able to learn more and dive deeper into what goes behind machine learning from real machine learning engineers. So I think this is a pretty good resource. And then here is Google AI's page. Now here I'll talk about ChatGPT because I was really excited about talking about all of that. But then yeah, so just see what all cool things they do and what all things are going on in the AI world. Because the video that I showed you, it's like 7 years old, and right now things are pretty cool, cooler than what it was before. And then here is the actual OG machine learning playlist by AnguNG. So if you like whatever material that we shared here has been coming from that, whatever courses that you find online have been like extracted from what AnguNG taught. So it's better to learn from the person who actually taught other people. So I think this playlist is a really good go-to, and he starts from the very basics of what machine learning is and how do we classify supervised, unsupervised, and then he goes deeper into linear and logistic. So depending on what you really want to explore in this exploreCSR program too, so whatever project that you're thinking to build, so maybe you come across, say you want to build a classification kind of a model, so you can just go onto this playlist and watch his videos to know more about different types of classification that I talked about today, and then you can just try and build those things out. So yeah, like coming back to the AI thing, I'll just open this page up. Another cool thing here is that Google's Bard and Google, like ChatGPT, which Microsoft took over, is actually built by Google itself. So ChatGPT is by Google and then Bard is by Google, which Microsoft took that over. I think it's okay. We just like, I'll just take 5 minutes.
No, it's not.
Little bit more. Okay, I'll just hold on then. Yeah, so like what I was saying is that, so what basically happened is like at the beginning, I also tell you how the way I told you like the letters A, B, and C and all these things were going. So how does ChatGPT and Bard, they're different in that logical computer science terms. So it's basically like, say, if I say that, say who's gonna win FIFA World Cup in like the coming coming years and something of that sort. So what ChatGPT does is ChatGPT works on transformer, which is like an algorithm or an architecture which Google created in some like 7 years back, 5 to 7 years back, and it was open source. So what OpenAI did, they built ChatGPT on top of that. They trained it on GPT-3, and then Microsoft took a huge chunk of OpenAI shares and then invested into that. So basically, ChatGPT-3 and then GPT-4, which is coming up, they all are built on Transformer, which is built by Google itself. So basically, it's like Google competing with Google. So Bard, on the other hand, is like a thing which they have created, which is slightly different from this entire Transformer thing. Why? Because it's trained on dialogue conversations. So for example, if I ask what's your name and then you answer your name and then we have a conversation here. So it's like a dialogue based thing. So how Bard thinks is you pass a dialogue here and it detects how to respond to this entire dialogue at once and then give you a dialogue and then put a dialogue there and then judge what the next dialogue would look like. So suppose you ask ChatGPT to write a code for like scraping the web or like building, say, adding 2 numbers, and it writes a Python code for you. So what Bard does, it takes it dialogue by dialogue, it parses everything by dialogue and it judges on top of that. But GPT-3 is only word by word. So it basically like predicts, say, I want to answer this. If you say, write me a poem or a passage on an essay or like my school or sort of thing. So what GPT-3 would do is it will just take one word and say the, and then it'll think, like what to put the next word. So maybe the person, then maybe like the third word tree, maybe next word this. So it all has to make sense for GPT-3 to predict these things. So this is how the supervised and unsupervised learning, they all fit into that broader scale of what things are working right now. And at the lower level, the word by word prediction is something which GPT-3 and every like transformer model does. And what BART does, it does a dialogue prediction. So at the end of the day, whoever wins, it will be like the model which are like competing with each other. So here in this entire session, when we talked about predictions and when we talked about machine learning algorithms. So whenever you are creating your own spam filtering and other things, you have the choice to choose what to do next. So in our case, we were trying to train it on an Excel sheet and we were passing zeros and ones there, and it was telling that, this is a spam, this is not a spam, just train and, give us the output. Maybe like a more complex world scenarios, you will actually be saying that if the user types, will it train today? You'll say yes or no based on the weather report, which is coming up from an API, and then you fit the next words together. So that is how the core machine learning goes. But in a very general sense, this is what supervised learning was, and you can just explore the resources at the end. I hope it was useful. Thank you. I'll just check the chat once if you have some questions. Do you have any questions? I'll be happy to take them now. Should we turn on the recording? Let's go. So I think if there are no questions, then let me see. There's something cool. So we have a lot of time to give you back, so I think we can do it. But yeah, I think just try and explore these things out. You have a lot of resources here which they've created. See, I think, okay, yeah, so here's the recommendation system. So it's like a 4-hour course and it helps you like build something. So it's better if you like build something while you learn, so that throughout the exploreCSR program too, at the end when you have to create your own project and to work in teams, you'll be able to contribute much better and you know how the machines are working, because this is pure mathematics and nobody can teach you how to write better algorithms, because that you have to explore it on your own. So thanks a lot. Bye.
Any questions on the demos? I think we don't understand